Hello, this is Graham, and it's Monday the 8th of July, and I thought I would talk about the Langton-Zant wave equation in its matrix form. So here we start with psi. This little psi here is the continuum. Classically, it's 65536 elements long. This is the delta, which indexes psi, and this has a value between 1 and 65536. This is the A coefficient and the B coefficient. You'll notice this is in quaternion form, and that's only so that we can use this as an energy equation. In the Langton-Zant equation, we set this to 0 and we set this to 0. So we'll go and quickly look at that, and then we'll look out and see why we have an A and a B coefficient for this equation. And so here we can see the 0, and we can see the 0 in the N matrix. Remember, this is the A, N, and T for multiplying out. I like this. This is not the A coefficient. The A coefficient has been explicitly put in here and here. So let's go and find out why we're using an A and a B coefficient. So this is the equation in two-line notation. We have a function that maps K into the complex plane, and K is bold because it is actually a vector, and it will have it'll have a position within the matrix. So it'll have 65536 elements as well. Remember, if the lattice is much bigger, K will have to adapt to that size as well. So the Euler identity is normally cos theta plus I sine theta equals e to the I theta. But we want an n in this to make it elliptical. And the way we do that is we use two-line notation, we use partial fractions. So here we have the half n plus 1, and we have the half n minus 1. And when you multiply this out, you get n cos theta plus I sine theta. Note that theta in this particular format is integrated on each step. So this is an integrator, and what we're doing is we're going to add to theta, we're going to add plus or minus 1, because Z is the continuum, that's the ant matrix, K is the index within that, and remember K has an index of T at a specific time. So, this is actually a tensor, but we don't worry about that too much. We just need to know that Z contains values of minus 1 and plus 1 in the lattice. And each time we iterate this, it just adds 1 to this, or minus 1 to this theta. And hence the wave number is pi upon 2. Interestingly, sometimes you'll see the wave number is pi upon 4, and the reason for this is that if you had a 3x3 matrix and they were all initialized with plus 1, then the sum, the what I call the Feynman path integral, the sum would be 9, because there are 9 elements with plus 1 in it. If you flip one of those elements to minus 1, then what happens is it sums to 8 with the older ones, but then you have to subtract 1, giving you 7. And that means that that by flipping a colour, you've gone from 9 down to 7, which will then go down to 5 if you do it the other way. So it's always steps of 2. So what you need to do is you need to take pi upon 2 as your 4 directions, and you need to divide that further by 2, because you need to half the sum. And this is why we have a priori and an a priori in one of the equations that I published. It did get a little bit messy, but this is the a priori, because what you're getting is you're getting information about the rotation and the color, but you don't know where the position is by analyzing the lattice. On this one, you know where it is, but you don't know. But you don't know what the next theta is going to be, because it hasn't done it yet. So it's very much similar for the Kalman filter. If you ever derive that from statistics. So that's covered that one. Let's go back. So in in this equation, we have the A and the B, which gives us the elliptical form. Now, E squared is just simply the size of the lattice, which will be 256 times 256 to give you 65536. And here we're summing up all the elements of little psi all the way from 1 to 65536. And the reason why this has got a delta in it and not n is because this is psi delta, which is not the same as psi theta, because this is the exp functions, which are right here. We have psi, we have the conjugate here. This is psi theta conjugate, and this is psi theta. And as you know, this is the solutions to a general solution to a wave equation. And that's why we put a little d on psi to say that this is psi d. And the reason I've called this psi d and not a normal one is because we are multiplying the exponentials, which means we are adding the indices. And psi delta is the little tiny delta changes that accompany psi theta. So as psi theta grows, psi delta is your spin angular momentum, and you have your angular momentum and position. Interestingly, with the a priori and the priori, it's you know where the ant is, but you don't know how fast it's going, or you know how fast it's going, but you don't know its position. So in some ways, it has that exclusion principle in there, uncertainty principle, where you don't know, you can't know both things at the same time. What else do we have in here? Yeah, interestingly, when you multiply this entire equation out, psi delta is squared with psi delta. So you've got psi delta times psi delta. And the reason why that is always plus 1 is because delta is the pointer. So this is the ant. It's pointing within psi, which is the continuum, and it contains values of -1 and +1. So of course 1 times 1 is 1, and -1 times -1 is also 1. So you're guaranteed that this will always be unity, which is why it just falls out the end and disappears. And it's the same for this one. Psi theta conjugate times psi theta always gives you 1. And for the very, very first iteration, if you're going to use the thing to find whether it's invertible or not, then AD minus BC is this will always be 0 on this trace, because if you've got 65536, take away 65536, that's 0, and this is always 1 when you multiply it out. So this will actually be e to the power of 4 when you multiply that out, a times d, and b times c is 1. Classically, what I've done is I've defined B and A to be permeability and permittivity. Sorry, permeability and permittivity, and I will show you how that works by going over to here. Now these are Maxwell's equations. These are the B over H curves for the thermal hysteresis curves of transformers, and you've got the same for the D over E for charge saturation. This when it's with the telegraph's equation in empty free space, so you don't have any physical resistances or impedances in there, it's just you're basically working with radio waves. Take that radio wave to its extreme at the speed of light oscillations, and then I'm saying that this is a core sample of space, and between these loops, which will be 256 loops with 256 elements each in it, you could effectively treat that as 65536 hydrogen atoms that are occupying space as a core sample, and you're just wrapping it up into this configuration. And because electric fields and magnetic fields are connected to each other, then the E plus 1 and the E minus 1, which we find in these coefficients for mu naught and epsilon naught, are saying that E, the capital E, which is the size of the lattice squared for this entire length here, is just one of the same things. So it's your electric fields and magnetic fields are just nothing more than the same phenomena. It's just one is a manifestation from the acceleration, and the other one is from a velocity. So you would put general relativity in here and special relativity in here to give you your total charge. I have done a video on this. It's a separate video. I don't think there's much more to talk about in here. So the fact that we're going from n equals 1 to e squared, and we haven't got n showing in here, is because this is the continuum, psi delta, and it should be indexed by n, but that should be self-explanatory. The reason why we're not seeing x in any of this, or t in any of this, is that t is actually the number of iterations, because we're going to integrate. And the reason why we got an x is because this is actually ex squared, because that is your first lattice. Normally this would be a capital X and you would have three lattices, and each one of a different size to give you a three-dimensional energy equation. And obviously your trace would be much, much bigger. And I've done a video on that as well somewhere. So this is for the normal hydrogen atom, this is a quarter wave. It's just the solution to a quarter wave equation, and hence we have 4 rotations and we can iterate it as many times as we want. Thank you very much. Thanks for listening. Bye-bye.